in machine learning. Thomas Dietterich is Distinguished Professor and Director of Intelligent Systems in the School of Electrical Engineering and Computer Science at Oregon State University, where he joined the faculty in 1985 after receiving his PhD from Stanford University. He served as executive editor of the journal Machine Learning, and then he co-founded the Journal of Machine Learning Research. His research interests reside at the boundary of computer science, ecology, and sustainability, as he is a part of the leadership team for OSU's ecosystem informatics programs. He has been quoted for his academic perspective in many major media outlets and authored many books, among them Readings in Machine Learning, published in 1990 with Jude Scholing. Thank you for accepting our invitation and for taking such an active part in our symposium. And now we are excited to give you a talk.
Well, it's a pleasure to be here, and I thank all of the Europeans for staying up late. We're straddling many time zones here today. My core expertise is the machine learning research and the machine learning community, and I guess I'm representing the sort of mainstream of machine learning today. And the points I want to make, I guess the first one is something that perhaps is already a consensus among the attendees today, which is that machine learning, or generalization in the way that we define it in our community, is impossible without imposing some innate restrictions on the space of structures to be learned. And then I want to take a brief tour through some different machine learning algorithms and talk about what the different restrictions are that they impose, because different algorithms impose different restrictions. And in fact, that's one of the reasons that in practical machine learning engineering, you often need to try several different algorithms to see if you can, and compare their performance on your problem. The third observation is that it's difficult to translate the restrictions that are in these algorithms into declarative statements about the world. And so we'll be kind of making contact more with the interactionist framework, perhaps, or the constructivist framework that we've been discussing all day, to say that it's really the interaction of these almost syntactic or mechanistic restrictions with the experience or the data that the system receives that leads to the outcomes. But then I want to talk a bit about the culture of the machine learning research community, because it's kind of allergic to innateness and definitely allergic to building in prior knowledge. So we'll talk about why that's true. And then I'll wrap up with just a little bit of discussion about some groups within the machine learning community that are pursuing various forms of innateness or generality. So let's get started with the first point, which is that generalization is impossible without innate restrictions. And I think Chomsky made a version of this argument probably 50, 60 years ago. But our definition of generalization is that after analyzing a modest amount of data, that a learning system is able to make correct predictions on additional data points that it did not see during training. And so let's consider the task of learning a Boolean function. So we imagine a Boolean function is a function that's defined over a set of Boolean input variables, 1 through D, and its outcome is also a Boolean variable, which I'll refer to as Y. So it's a function that maps from these D-dimensional inputs to one-dimensional Boolean output. Now, it turns out there are 2 to the D Boolean functions that can be defined over D variables. And so if we make no restriction at all and consider all of those doubly exponentially many Boolean functions, it turns out that we really can't generalize successfully until we have seen all possible data points. And the argument goes something like this: if we consider a single training example, as we call them, right, we see it's a particular vector 1, 0, 0, 1, 1, whatever, and the output is 0. That training example will be inconsistent with half of these Boolean functions, the half of them that label the output 1 when it should have been 0. But this means after seeing n data points, we will still have 2 to the d minus n consistent functions. So this means that to get ourselves down to having only one, to sort of proving to ourselves the one true function, we would have to see 2 to the power D training examples. And so we really cannot generalize without seeing all the data. But suppose we impose a constraint. For instance, we might assume that the function we're trying to learn is represented by a linear threshold function. So this would be, right, a sum of terms, each with some weight, real valued weight, say, multiplying them, and then compared against a threshold value. Now, it turns out there are only 2 to the d squared possible linear threshold functions that represent that are distinct Boolean functions. They can be represented in many ways, but there are only 2 to the d squared distinct Boolean functions. So this means we only need to observe quadratically many data points to find the true function. And so we can generalize successfully. Okay, well, let's take a tour then and look at different machine learning algorithms and ask what constraints they do impose, and maybe try to draw some connection to what assumptions they're making about the environment. So, of course, linear models have been around for a very long time, and they're basically making an assumption of linear additive effects. So, in machine learning, really following on some analysis from Bernard Scholkoff's group and before him, David Heckerman's group, we like to ask, well, what does it mean in the causal and in the anti-causal direction? So in the causal direction, what we mean is we're thinking of a phenomenon where these x1 up to xd are potential causes of the outcome y. So they might be, I don't know, diet and exercise and smoking causing a disease or preventing it. And we also think in the anti-causal direction, that is, suppose that y is the disease, but now the various x's are symptoms of that disease. So this would be something like blood pressure, maybe, blood sugar, who knows, these kind of symptoms. So in the causal direction, a linear model is assuming that there is an independent effect of each of these causes. And the alpha variable is basically giving the strength of that causal effect. In the anti-causal direction, it's assuming that each of the different symptoms of the disease is being generated independently. That the only reason that a person that has both a high fever and body aches is because they're caused by a common disease, but each symptom would occur independently of the others. Whereas in the anti-causal direction, we're assuming, so I said that. Okay, so very often we, in addition to making this additive effects assumption, we also impose variable selection, right? So we want to prefer models that have fewer variables in them over models that have more variables. And this is a kind of Occam's razor, I guess, or a simplicity kind of bias. But if the variables are candidate causal factors, then this becomes an assumption of sparsity of causation, that y has only a few causes. And in the anti-causal direction, it would become an assumption of sparsity of effects, which might be a somewhat strange assumption to make, but it could be done there too. Okay, well now let's move to another very popular machine learning algorithm, decision trees. And the fundamental assumption here is that we're going to dispense with independence. We will be looking at interactions among the variables, but the assumption is that the input space can be partitioned into regions, and in each region only a small number of variables account for the output. So we have interactions, but they are perhaps only apply locally in regions. So that's the decision tree kind of assumption. Nearest neighbor methods are very popular, also known as case-based reasoning methods. Right? In this case, we imagine, say in this picture here, that one axis might be, I don't know, blood pressure, and the other may be temperature. And maybe we have 3 things we're just trying to discriminate between: healthy patients who are green, red patients maybe have heart disease, and blue patients maybe have a cold or something. And so when we get a new patient in, we just ask, well, what are they most similar to? And unlike the sophisticated notions of similarity that we were just discussing, here the usual practice is to just compute the Euclidean distance between the featurized representations of our patients in this case. So because the black dot is closest to a green dot, we might hypothesize that this is a healthy patient. Of course, that might be a little risky, basing your assumption on or your conclusion on only the nearest neighbors. So you could take, say, the 11 nearest neighbors in some region, some disk around the black dot, and have them take the majority vote of that evidence. But the thing to notice here is that every attribute of the patient in this case is given kind of equal weight when we compute a Euclidean distance. They're all treated as relevant and assumed to be independent. Then, if there are correlations among them, then we need to do things like principal component analysis to try to rotate and change the coordinate system so that we can make those different dimensions orthogonal to each other. Convolutional neural networks. So what assumption are they making about their task? Well, the assumption here is that basically the outcome is determined by a combination of features, and those features are extracted from the image by looking at regions at various scales. So the idea of a convolutional network, right, is that we have a small so-called kernel or a little small model or filter that we scan across the entire image, and that produces a sort of virtual image that says how strongly this kernel was turned on in each spot on the image. So a kernel might be something that's looking, for instance, for a horizontal bar, and so it would be triggered by the legs of this zebra, but really nothing else, maybe the mane also here. And maybe another filter, which would be in one of these other layers here. You can see these multiple planes, they're called channels. Might be tuned for vertical bars and another one for diagonal bars and so on. So you can learn a lot of these. And then activations that were near each other are often pooled to form a single activation at a higher level, and then kernels are applied to those pooled values. And this is repeated so that when we have a region here, that corresponds to quite a large area in the original image, but it's being applied to the results of these previous activations. So this produces then a vector of these so-called features that are present or absent at various places in the image. And they are gradually delocalized spatially as we move deeper, so that by the time we get here, most of the spatial information has been discarded. And then there is a more or less standard classifier. Usually it's just a linear model here to move to the final classification decisions. But an important thing about these deep networks is that we are also fitting them using stochastic gradient descent. And we've already had at least two previous speakers, both Alison Gottnick and Melanie Mitchell, have pointed out that there is sort of a notion of temperature and stochasticity in these optimizations. So this isn't really simulated annealing, but it has much the same character that when we have a very high learning rate in our stochastic gradient descent, it bounces around a lot. So you have to imagine a landscape where each location in the landscape corresponds to settings of the millions of weights that make up this network. And as we move around in that landscape, we are changing the weights in the network. And the height of the landscape is some measure of the error or accuracy of this network on the task it's been given. So we want to find a point with very low error. So we want to find a very low point in this landscape. Stochastic gradient descent tends to find large, low, flat plains or plateaus rather than narrow, deep valleys or even deep holes like a well or something in the landscape. And this flatness seems to be a very important aspect of what allows them to generalize. The flatness is maybe only local, but when the response of the loss function is very flat, that means that you can be making changes to these weights, or more importantly, changes to the input image that do not change the output. So if we slide this zebra around, or maybe twist it a little bit in or out of plane, we'll still get largely the same response. If we flip it upside down, maybe no, but these are generally robust to changes particularly in translation and scale, but others as well. So there's still a big mystery about exactly why they perform as well as they do. because these networks have many more parameters than the amount of data they're trained on. Even though they're trained on millions of data points, they have billions of parameters. Okay, well, the last example I want to show you is more recent work on human-object interaction networks. And these are pictures from a data set called HICO, which was developed at the University of Michigan by Chow. But the system I'm most familiar with that works on this problem is from Australian National University by Steve Gould's group. But the idea of these networks is they make an assumption along the lines of the objects in an image have a spatial locality, and that a person interacting with an object has a typical spatial relationship with that object. So, so in this case, the idea is that in each of these images, there is a triple of a person interacting with an object, and there is some kind of interaction, which we might think of as a verb. So the child is eating the apple, the boy is feeding the horses, the person is riding the bicycle, they're washing the bicycle, they're washing the horses, they're washing the apple. So there are various, combinatorial combinations are possible. And the goal is to have trained on a collection of images that are annotated by drawing boxes around the object and around the person, and then a line that connects the centers of those boxes to each other. And so the network then actually detects these objects, learns to detect the objects, then and draw boxes around them, and then extracts some features that describe this relative displacement of the person from the object. Is the object completely overlapping the person, or is it mostly disjoint from the person? And so it can basically implicitly learns things like, if you're eating something, it needs to be near your head in some sense, right? And here he's feeding the horses. You can barely see the carrot that's being fed to the horses. And I don't know that the network sees that carrot at all. I think it just sees the poses of the human and the horses and guesses that this is a feeding verb. But it's interesting to look at, this is starting to get closer to the things maybe that Spelke and Gottmik are studying. Okay, so I guess zooming out a bit, I want to point out that most of these constraints and preferences are expressed mechanistically in terms of operations on the input variables, preferences for fewer versus more weights, weight magnitudes. They don't really make ontological or causal claims about the world. And I think this is very compatible with the whole interactionist program, and particularly with Gregory Cohn's talk earlier today, that the success of these systems really relies on exposing them to very carefully curated data. And maybe that's similar to the ontogenic niche that he mentions in his abstract, but actually didn't discuss in the paper this morning. But we did discuss the idea that development is relying on reliable features of the environment as part of the developmental program. These learning algorithms are certainly relying on the particular properties of the data that they're being exposed to. A big challenge, I think, in machine learning is we're struggling to find the right kinds of constraints or structures that would enable systems to learn about objects and relationships and agents and processes in a three-dimensional and social world. A part of the issue there is computational tractability, because when we start reasoning about relationships and objects and their relationships, now we're reasoning over graphs. Even this human object interaction data has little graphs in it. But when we reason about agents, well, then we need to reason about their goals, beliefs, preferences, intentions, actions, the consequences of those actions, and so on and so forth. So a huge number of hidden quantities. So that's part of the challenge, I think. Now let me turn to the sort of culture of the machine learning community and why it is kind of allergic to even discussing innateness, and certainly to discussing prior knowledge. So as a kind of engineering enterprise, the goal of machine learning is to replace handcrafted programming with automated learning. And if you take that as your objective, then if you require more handcrafting to design the right innate structures, to build the conceptual knowledge that the system needs, then you're somehow failing in this enterprise, right? Even though the result would be the system could learn from much less data. So from an engineering point of view, it still might be desirable, but it's just counter to the culture. And so I think this has discouraged research on innateness, and it's led us to a situation that we all are aware of, where we're training these massive networks on massive amounts of data points at massive expense. So it's costing millions of dollars in computer time to train these large language models and these combined vision and language models. But I think somewhat paradoxically, when we see research on these deep learning architectures, such as the architecture for this human-object interaction, people are really studying innate mechanisms that might be helpful. And there is a sense that we're maybe uncovering sort of design patterns for how to build good deep learning systems. Well, of course, the machine learning community is also very much motivated by trying to come up with general purpose mechanisms. We would really like to have, some sort of engineering methodology that lets us take our machine learning method off the shelf, remove the shrink wrap, and apply it to a new problem without having to do a lot of work. Work meaning modeling, putting in background knowledge, and so on. But I would say there is a distinction being made in the machine learning community, and maybe it will be interesting to explore this in the discussion today, between what we might call innate mechanisms on the one hand and programming on the other. I'm confused about this myself, so but let me try to draw it out a little bit. So the idea of these innate mechanisms is that they would not need to be changed as we move from one task to another. Whereas in programming, we would need to make some kinds of changes, but maybe we can make them in a very high level language where that programming language does not need to change. Maybe that programming language is operating in some cognitive architecture or neurocognitive architecture that does not need to change from one problem to another. While the innate mechanisms typically cannot be translated into statements about the world, at least not easily, the programming style generally can be interpreted as providing some kind of content. It may have, content in terms of logical propositions or particle hierarchies, type, subtype hierarchies, and so on. A lot like what we just saw with Copycat. So just let me talk about three paths that people have been pursuing. The first one, and perhaps a very intriguing one, is really the research group led by David Silver at DeepMind in London, where they have been pursuing the following methodology. They first built a reinforcement learning system for a single task, which was playing the game of Go, and that was the AlphaGo system. And they set their goal was to build a system that could perform at superhuman levels, or at least at the level of the best humans. And so they succeeded, obviously, with AlphaGo. But then the AlphaGo system actually relied on a corpus of human games between expert Go players, as a way of initializing the process, which then switches to a self-play where AlphaGo plays a copy of itself and tries to bootstrap itself up to play better than the humans could. And the intuition of the team was that if we remove this dependency on human games, it might play even better than humans. It wouldn't be held back by human misconceptions about optimal play of Go. And this turned out to be the case. So they built a system called AlphaGo Zero that no longer depended on these supervised training on human games. From there, they then said, well, can we generalize this by taking on other tasks? We want to have a single learning system that we don't need to change anything in it in order to play Go or to play chess or to play shogi. So for each of these games, it would be starting at the same initial state, but now given access to a simulator that simulates or plays the actual game. So the simulator says, here's what the board looks like, literally as an image. Here are the possible actions you can perform, which to the system look like buttons you can push, or just numbers. They don't have any semantics, except what happens when you push them and the simulator simulates. And finally, here's the objective of the game, is to, get this final reward. And so that led then to AlphaZero, which was able to play like that. Now, along the way, they've had to strip out things that turned out to be ad hoc, either ad hoc for Go or and so on. And their most recent move, and generalize what they had there. So their most recent iteration, right, is this system mu0, where they wanted to generalize further. All of the alpha systems relied on being able to repeatedly invoke a simulator that knows the rules of the game and can play the game forward. mu0 has to learn the rules of the game. So it starts not knowing anything except, here are the different buttons you can press, and here is the objective. You're trying to get this reward. And everything else has to be learned. So they view their goal as really finding a sequence of steps of various, increasing challenges that challenge the breadth of the set of things that can be done, that need to be done to be achieved, that will eventually lead them to human-like agents that could perform well in a physical and social world. So I guess any piece of innate structure that they build in needs to be justified by the fact that they need it in order for the system to succeed in these more general contexts. So that's kind of their research program. An alternative research program is a top-down program. And this has a long history too. And the goal here is to somehow express prior knowledge in a way that can be taken up by the learning mechanism. So how can we combine prior knowledge with learning? So some of the early work was knowledge-based neural networks by Jeffrey Tall and Jude Shavlik back in '94, where they translate assertions in propositional logic into constraints on network weights. Then they can do learn on data, and then they can extract out updated propositional logic rules. In my group, we studied something where we were interested in imposing monotonicity constraints on learned functions. We wanted to say, the hotter it gets in Oregon, the more likely it is that you'll have wildfires, or those kinds of monotonicity constraints. Those didn't really have much of an impact on learning. It turns out that a lot of those monotonicity relationships are super easy to discover from the data. I'd say two more recent and very exciting directions are probabilistic programming, which again has been mentioned today. And so the idea here is to provide a high-level programming language in which it is very easy to express rich probabilistic models that may involve latent objects and relationships, dynamics, all kinds of things, and then the processes that are the observable consequences of those. You build a model, you can put prior probabilities on it, and then you can press the go button and learn from data and make inferences about your posterior distribution. So probably the best, the most widely used is the statistical language STAN. That's Carpenter et al. Here. But then there are others that are based more on more computer sciencey type of languages, Lisp-like languages, and where you can basically you're writing a probabilistic program that each time you execute it, you get a different random path through the space, and then you say, well, the outputs, when I run the system, the outputs should look like my data. Now figure out the free parameters in this program that will cause it to generate the data that I'm seeing. And another very exciting area is physics-informed machine learning. And so I need to add the bibliography for this talk, but Karnadiakis and colleagues had a paper recently, I think in Physics Review Letters, where they talk about solving a difficult system of differential equations by using a neural network. And the goal is to have the network when it has minimized its objective function, its loss function, that the resulting surface that it has learned is the solution to a system of differential equations. And the sort of training data that they give it are boundary conditions. They sample along the boundary and say, here are the values here and here and here. And also some so-called collocation points in the interior of the space where they enforce physical laws at those points. So, conservation, for instance. And then they use, stochastic gradient search to minimize some loss function that they've defined. And at the solution, they get these networks out. And they're able to solve differential equations that have been extremely challenging to solve prior to this time. So maybe you can get this sense that I don't know whether I would count this as innate knowledge or not. It's innate in the sense that it is prior to observing the data, but it has been programmed by a person who can insert relevant background knowledge into the system. And so the program has much more this feeling of a model as opposed to a mechanism similar to, say, our baby chicks whose auditory system is influenced by the sounds they hear when they're in the egg. Okay, well, the last thing I was going to mention, and has also already been mentioned by Alison Gopnik, is the DARPA Machine Common Sense program. I'm not involved in that program, but my colleagues here at Oregon State are. And as you heard this morning, the goal is to create an AI system that can learn the common sense knowledge that a toddler has from simulated experiences. And so the idea is that the grantees in this program need to build a simulated common sense agent, and then that agent will be evaluated by giving it in a simulated environment in which it can watch things happen in video, it can take actions, make predictions, form expectations, and have these experiences. And then it's basically evaluated somewhat along the same methodology that's used to evaluate the knowledge that infants and toddlers have, which is in terms of signaling violation of expectations. So the system signals when its expectations are violated. And these systems are supposed to learn all these kinds of things. So I guess the premise of this program is that we can somehow shortcut all of that evolutionary stuff and try to build a system that can acquire this core common sense knowledge from these kinds of experiences. So I'm not sure where that fits in this would be then the innate knowledge, I guess, that we would think maybe these young children have, or would it be, or is this, or will it be the constraints that need to be built into these systems that would be the innate structures that will enable these simulated children to learn very quickly in this test environment? But I don't know. I think we'll learn something either way. But as far as I know, there aren't very substantial results yet. The program is still less than halfway through, I think. Okay, well, let me summarize then. I tried to take you on a little tour through some machine learning algorithms and show you that these different methods impose different restrictions, but that these restrictions are mostly stated at a mechanism level rather than being statements about or claims about the world. And then I discussed how the culture of the machine learning research community has viewed innateness as a kind of necessary evil to be minimized to the extent possible. And then discuss some of the current research programs that maybe are making a more concentrated run at the innateness problem in machine learning. So the DeepMind path, the top-down programming approach, and then this machine common sense program. And so with that, I will stop and answer questions.
Thank you for the talk. Do we have any questions?
Yes. Yes. So actually, I wanted to ask. So you say that actually there is no, in a way,
unified way of like, let's say, defining innateness in AI. So there are like different constraints in different types of models. So actually, at the beginning we were discussing if innateness is actually a coherent concept, a concept that has like some coherent meaning, or it's basically a bunch of different concepts that can be related to each other. So do you maybe have impression that in terms of that in case of AI we have similar problem, that we in fact maybe have different meanings of innateness, and we just sometimes use this word to denote all of them? Maybe like speaking about the architecture would be better than.
Yes, I don't know. Yeah, so I would agree that, well, for one thing, I would say the machine learning community generally just does not use the word innate, right? Instead, we talk about maybe priors, if we're thinking about it as a Bayesian kind of strategy, or we call them biases, which is maybe an unfortunate word to choose, but the idea is that it's a preferences for some parameters or models over others. I think the machine learning community has not thought in a careful way about this. But if we judge the community by its actions instead of its words, it seems clear that people are hoping that they will find some small core set of architectural constraints that will apply across a wide range of settings. And so that is assuming that there is some kind of innate structure that will be sufficient. Other researchers don't really believe that. I would say that, Gary Marcus and also, Joshua Tenenbaum and would argue that that's, unlikely to be fruitful, let's say, as a research program, and that we should build systems that let us do better modeling. So you could imagine, for example, if Josh Tenenbaum were here and was saying, well, let me see if I can take Melanie's stuff and write a probabilistic program that could explore a space similar to what she's doing. So he would hope to unify the various different, kinds of things that need to be learned into some maybe grand probabilistic program. I don't know. My criticism of the probabilistic programming mindset is that it still feels too much like programming and not enough like architecture. But I don't know. Our trip through the history of the brain today showed that that's quite a complicated and inelegant but carefully structured system. So I just don't know where we stand, really. Yeah.
There are no more questions. Actually, I want to ask one more thing. There was this paper that I mentioned at the beginning, and that was mentioned a few times, written by Tony Zader, who claims that we should have a look at animals, how do they organize their behavior, and if we look at animals, we see that there's some part of this repertoire is innate. And actually, are there like any bio-inspired algorithms that actually try to do it, like that they are successful? So like they take inspiration from I don't know, like the way animals behave, and they implement some sort of like, I don't know, like instinctive behavior that you find especially, I don't know, it's like surprising or.
Well, obviously reinforcement learning, evolutionary algorithms, genetic algorithms, these have all been inspired by biological models, but they are themselves terrible biological models, right? They don't deserve to be taken seriously as biological models at all. In fact, I mean, we saw that in the talk on the network structures by Sebastian that the genetic algorithm was serving primarily as an optimization algorithm that has certain desirable properties, but functionally it wasn't to be taken seriously as an evolutionary model. And reinforcement learning obviously is very different from well, not, I mean, we do know that there are some processes in the brain that are very well modeled by some reinforcement learning algorithms. So there are some cases where it can be taken seriously as a model of neural computation, but more generally, it's a very impoverished model of how animals and people would learn. So yeah, we just have trouble with, I mean, I guess maybe in some sense the whole machine learning field would prefer to study simpler settings where we can understand what we're doing before we tackle more complex ones.